Hello students, lecture on dual nature of radiation. We will talking about electron emission. As we know that the metal have free electron that conduct electricity. If these electrons come out of the metal, then the metal surface acquire positive charge and attract the electrons back to the metal. So normally the free electron cannot escape out of the metal surface and are held inside by the attractive forces of the ion. Now thus a certain minimum energy is required to pull the electrons out from within the metal. This energy is known as the work function. If you want to escape these electrons from the metal surface, this is a metal surface, then the required minimum energy, the minimum energy required to pull electrons from out within the metal is known as work function and is denoted by phi, symbol phi. Okay, and is measured in electron volt, small e electron volt. The value of 1 electron volt is given by 1 electron volt is equal to 1.602 into 10 raised to power minus 19 coulomb. That is the value of 1 electron, and 1 volt is volt. So if we multiply these two, then we get 1.602 into 10 raised to power minus 19 coulomb into volt is becomes joule. Okay, then 1 electron volt converted into joule is 1.602 into 10 raised to power minus 19. Okay, now the work function, that is the minimum energy required to pull electrons out from within the metal surface, depends on the property of metal and the nature of its surface. That what type of metal, that is like zinc, copper, or any kind of alkali metals like sodium, potassium, and other. Now the minimum energy required for electron emission from the metal surface can be supplied to the electron by any one of the following method. The first one is by thermal emission. Thermal emission means by suitably heating, sufficiently thermal energy can be imparted to the free electrons to enable them come out of the metal. The second one is by field emission, like electric field, magnetic field, by applying a very strong electric field of the metal surface. And the third one is photoelectric emission. These three are the ways of energy supplied to metal surface. For what? To pull out the electron from the surface. And the third one is, that is photoelectric emission. Okay, when light of suitable high frequency means ultraviolet, when a light of high frequency shines on the surface of a metal, this is metal like zinc. If ultraviolet rays that high frequency, if the high frequency shine on a surface of metal, it emits electron. The photo generated electrons are called photoelectrons. These are known as photoelectrons, and the phenomenon is called the photoelectric effect. Okay, now photoelectric effect. Okay, when zinc plate, another example, when zinc plate is eliminated by ultraviolet rays. Ultraviolet rays, that is high in frequency, it emits negative charge particle. It emits negative charge particle, that is electron, and develop a positive charge. Then zinc plate develop a positive charge within it is okay. The emitted electron are thus termed photoelectron, as I said before, and the photoelectric effect involve conversion of light energy to electric energy. That is light energy. Ultraviolet is light energy, and what photoelectric effect does? Converted it into electric energy. That photoelectric effect. And the electrons, that negative charge particle which emits from a metal surface, converted into current, electric current. So certain metals like zinc, cadmium or magnesium are basically responded only to ultraviolet rays. They are responded to ultraviolet rays, high frequency rays, while some alkali metals such as lithium, sodium, potassium, cesium, rubidium are sensitive even to the visible light. Visible light means Vibgyor pattern, which we can see. All these photosensitive substances emit electron when they are illuminated by light. For different wavelength of light, some photosensitive material gives different responses. Now, ultraviolet light rises to photoelectric effect in copper, while green or red light does not. Like if I am talking about the copper, then ultraviolet light give rises to photoelectric effect in copper, while green or red does not. Same, if I am talking about the visible light does not show photoelectric effect for copper, because copper needs high frequency rays, that is ultraviolet. Okay. Photocurrent. So there is an experiment for photocurrent. The experiment consists of an evacuated glass tube, that is the tube having a photosensitive plate C cathode and A anode. The monochromatic light radiation of sufficiently short wavelength passes through the window W, okay, and falls on the photosensitive plate, that is cathode. Now the transparent quartz window is sealed on a glass by a quartz window, sealed on a glass by flash. Okay, the electrons are emitted by cathode and are collected by a plate anode A. Emitted by cathode and collected by A, which flow through the circuit and back to the cathode. Okay, which flow through the circuit and back to the cathode. Now, the electric current is established in the circuit from A to C. If electron emits from cathode and collected by anode, the electric current established in the circuit from A anode to C. This current is known as photoelectric current. Why it is named photoelectric current? Because the source for this current is photoelectrons, so named photoelectric current. Now the photocurrent can be increased or decreased by varying the magnitude and sign of the anode potential with respect to cathode. Okay. Now the intensity and frequency of the incident light. Incident light can be varied, as can the potential difference also between the C and A can affect the photoelectric current. So there are three factors. The first one is intensity of light. Second one is potential difference between A and C, and the third one is magnitude of potential and nature of photosensitive plates. Photosensitive plates that are anode and cathode. Now, it may be noted that at a certain minimum negative potential, if the potential between A and C, or we can say the potential for C, certain between negative, okay, then the photocurrent becomes 0. If the potential becomes negative, that is known as cutoff voltage also, or known as stopping potential. If the potential becomes negative, that is known as cutoff potential or stopping potential, then photocurrent becomes 0. We will discuss this into our next section. So now, the intensity of variation. When the collector A is maintained at a positive, check here, when the collector A is the collector because it collects the emitted electrons from emitter C. When the collector A is maintained at a positive potential with respect to emitter C, the electrons eject from C are attracted towards anode A. If this is more positive than the cathode, then the electrons attracted towards the A. Now the frequency of incident radiation and the accelerating potential are kept fixed, and the only intensity of light is varied. Intensity of light between these is varied. Now the photocurrent increases with intensity of incident light. If incident light is increased, then the photocurrent also increases, because if incident light is increases, then the electrons emits from a surface also increases, and if electrons increases, then the photocurrent also increases, since photocurrent is directly proportional to the number of photoelectron emitted per second. Okay, now hence for a given photosensitive material, that is zinc or copper or any else, and frequency of incident radiation, the photocurrent is directly proportional to the incident light. This is graphically represented by the graph like this. Because this is cathode, this is anode. Okay, now incident on cathode, and the electrons emit from cathode, and the collector, that is anode, collect them. If the incident ray increases its frequency, then the electrons emits from cathode or emitter increases in numbers. Number of electron increases. If number of electron increases, then the magnitude of current is also increases, because current is number of electron in a specific time. If number of electron increases, then current increases. Hence we can say that current, photoelectric current, is directly proportional to the intensity of light. Okay, now the plot between photocurrent, that is the photocurrent, and that is the anode potential. anode potential V, that is retarding potential. As I have talking about that if the potential becomes zero, we can say that stopping potential or cutoff potential, then the current becomes zero. Okay, at a certain potential, the maximum negative potential at which current zero is known as the stopping potential. This is known as the stopping potential. The definition for stopping potential is that the maximum negative potential at which photocurrent is equal to zero. Okay, now for a metal, for a certain metal, if the intensity is I1, that metal, that is I1, that is I2, and that is I3. The plot of photoelectric current against the anode potential for different intensity of incident radiation. If the intensity I3 is greater than I2, I2 is greater than I1 as seen from the diagram, then this is the stopping potential, the maximum negative potential at which the photocurrent is equal to 0. Now for I3 intensity, the current photocurrent is maximum. For I2, the photocurrent is like this, and for I1, photocurrent is minimum. Photocurrent is less than from I2, I3 and I1. These three are the intensities. Now this is clear from the plot that if we increases the intensity of light, the photocurrent also increases. This is the important plot you have to remember for any kind of exams. Thank you for watching this video.